Hi guys. So today we're going to start on section 6.6. So we're skipping section 6.5 for right now because it's about exponential growth and decay, and we're going to do that section at the end of the course when we talk about an introduction to differential equations. So for now, what we're going to do is we're going to move on to an important new family of functions, which is the inverse trigonometric functions. So one of the problems with asserting that a trig function has an inverse is that a trig function is not a one-to-one function. The graph of y is equal to the sine of x, for example, is pretty obviously not one-to-one because it has periods. So there's no way that this could be one-to-one. After all, it grossly violates the horizontal line test. You can see that any line that you draw between 1 and -1 is going to cross through this function an infinite number of times. So this is very seriously not one-to-one. This is not one-to-one. And so, at least with its full domain, it doesn't have an inverse. So the trick is that we're going to restrict the domain to make the function one-to-one. And the usual restriction that we make is we take just a part of the sine function that starts right here and ends right here. So this right here is a restricted sine function. So it's got the same formula. You still say y is equal to the sine of x, but you make the domain to be between minus pi over 2 and pi over 2. And then, like usual, you go through the entire range of the sine function here. You go from -1 to 1. So with that restriction, now we have a function that's one-to-one. And a one-to-one function has an inverse. So when we talk about the inverse of the sine, we mean the inverse of this sine. Let's write down what our sine function looks like again. So the sine that we're dealing with is this part between negative pi over 2 and pi over 2. That's 1, and this is -1. So its inverse, y is equal to sine inverse of x, or sometimes we'll see the notation y is equal to arcsine of x. This is a function that takes this graph and reflects it across the line y equals x. So what we're going to get is a function that looks like this. And now this is pi over 2, this is minus pi over 2, and this is -1, and this is 1. Because remember, the x and y values flip places, and so the domain and the range flip places. So if the domain over here was from minus pi over 2 to pi over 2, then that means that the range over here is from minus pi over 2 to pi over 2. And the range on this side was all the values between -1 and 1, which means the domain over here is all the values between -1 and 1. So the easiest way to think about what an arcsine is doing is it reads a number between -1 and 1 and then tells you the angle that that came from. Okay? So sine takes in an angle and spits out a y value of a coordinate on the unit circle. The arcsine takes in a y coordinate on the unit circle and tells you the angle that it came from. So the relationship here is just like before. We say that x is equal to the inverse sine of y whenever y is equal to the sine of x. So the arcsine is the function that undoes the sine with this restricted domain. Sine takes an angle and spits out a y coordinate. So the input here is an angle, and the output you can think of as a y coordinate. And the arcsine, or inverse sine, takes as its input a y coordinate, and it spits out an angle. And that perspective is going to be important when we start deriving some of the properties of the inverse trig functions. So one thing you might be asked to do is to evaluate an inverse sine. And here we're going to use this relationship to do that. So if I tell you, find the inverse sine of -√2/2, what I mean is, if this is equal to x, remember that x here is an angle because angles are what come out of the arcsine. And the angle is the angle that if I put it into the sine, minus root 2 over 2 would have come out. So the equation I'm really trying to solve here is the sine of x is equal to minus root 2 over 2, but subject to the restrictions on the domains that we've been talking about. Normally, this equation has infinite answers because there's an infinite number of values of x that make this true. When we're dealing with the relationship between the sine and its inverse, on the other hand, there's only one value that makes this equation true. And we know that it has to be between minus pi over 2 and pi over 2 because the outputs for the sine function have to be between minus pi over 2 and pi over 2. It turns out to be the case that the x that does this between negative pi over 2 and pi over 2 is x is equal to minus pi over 4. It's important that when we get an answer with an inverse trig function that we look to make sure that the answer that we got is in the correct interval. So we need to do some calculus with inverse trig functions. They're going to turn out to be really important in some really fundamental types of integrals that are going to come up. And so that means we're going to need to know their integrals and their derivatives. So the question we want to answer is, what is the derivative of the inverse sine of x? So the way we think about that is with implicit differentiation. And we're going to notice a relationship here that's important. So remember that the sine inverse of y is equal to x whenever the sine of x is equal to y. So let's write down the equation, or the functional equation. Y is equal to the inverse sine of x. Now I can apply the sine to both sides of this thing. And what I'm going to get is the sine of y is equal to x. Now let's use implicit differentiation on this thing. D by dx of the sine of y is equal to d by dx of x. So the derivative on the left-hand side is going to be equal to the cosine of y times the derivative of the inside, which is dy dx. And on the left-hand side, we're just going to get the derivative of x, which is 1. Now I can divide both sides by the cosine of y, but this doesn't seem very useful. After all, I've got dy dx and this cosine of y on the right-hand side, and that doesn't give me a function in terms of x. And the original equation we wrote down was a function in terms of x. So somehow we've got to take this cosine of y, and we want to write down cosine of y as a function of x instead. So one way to do that is to notice that we still have the Pythagorean relationship that the sine squared of y plus the cosine squared of y is equal to 1. So there's one of your basic trig identities. And if we solve that for the cosine of y, we get cosine of y is equal to the square root of 1 minus the sine squared of y. But what is the sine squared of y? Right? What is sine y? Well, sine y is equal to x. So this is just the square root of 1 minus x squared. And what that means is that we get an expression for the derivative that looks like this. 1 over the square root of 1 minus x squared. So the upshot of this computation is that dy dx is equal to 1 over the square root of 1 minus x squared. And that's our first rule of derivatives for inverse trig functions. So rule 1 is dy dx of the inverse sine of x, which remember can also be written as dy dx of the arc sine of x, is equal to 1 over the square root of 1 minus x squared. Similarly, you can write down an expression for the derivative of the inverse cosine of y. And what you're going to end up with here is the same type of expression. So if you want an exercise, do this one. And you can do it with the same sort of argument we used here, where we start with this expression, we reverse it into an expression of cosine of y is equal to x, and then we use implicit differentiation, and you can end up with the same exact kind of expression for the derivative. The sine and cosine inverse functions are derived very similarly to each other, and we still have to make the same sort of restriction on the domain of the cosine. So in order to get a cosine that we can invert, so a cosine looks like this. So this is y equals cos x. Here, the restriction that we make looks like this. There's no reason why the function has to be increasing. It could also be decreasing. And this is the most basic domain that we can make for the cosine function that gives us a one-to-one function. So for the cosine, what we do is we restrict the domain to be numbers between 0 and pi. And the range is still all the numbers between -1 and 1. So we still get a full set of x coordinates. And so now, if I want to look at the inverse, y is equal to arc cos of x, or cosine inverse of x, then the domain is going to be like before, all the numbers from -1 to 1, and now the range is going to be values between 0 and pi instead. So that might seem confusing. You have to memorize two different domains and two different ranges for the two different inverses, arc sine and arc cosine, but it's not so hard if you can just visualize what the graph looks like, that you're looking for a piece where you can be one-to-one on this piece in sort of a maximal way. So what about the other trig functions? Of the remaining trig functions, the most important is the tangent. So how about y is equal to the tangent of x? Then we can define the arctangent by writing down x is equal to the arctangent of y whenever y is equal to the tangent of x. And just like before, we've got to figure out what the domain and the range of this relationship is, because tangent has a similar periodic structure. So a graph of the tangent looks like this. It has asymptotes all over the place, and those asymptotes are located at pi over 2 and 3 pi over 2 and minus pi over 2 and minus 3 pi over 2 and so on forever. And the tangent lives in these branches that sit between those asymptotes. So in order to get a function that we can restrict to be one-to-one, it should be pretty easy to notice that this function right here, this branch of the tangent, goes through 0, which is nice to know that the tangent of 0 is 0, and also it's one-to-one as long as I don't get outside of the asymptotes. So what I do is I make the restriction on the tangent that the domain that I'm interested in will be from minus pi over 2 to pi over 2, and that now the range is actually going to be all the numbers between minus infinity and infinity, because this function goes up forever as we hit the asymptote and it goes down forever. So we should think about what a graph of the arctangent must look like. Because remember, all of the x behavior and the y behavior switches places. So what is the arctangent going to have to be? Well, if the x values of the tangent can't ever get outside of negative pi over 2 and pi over 2, then the y values of the arctangent have the same asymptotes. So this is y is equal to pi over 2, and this is y is equal to minus pi over 2. And the arctangent sort of sits in between those horizontal asymptotes now, where every value between minus infinity and infinity makes sense. But now we get the fact that the limit as x goes to infinity of the arctangent is pi over 2. And the reason that's true is just because I can approach pi over 2 with x's over here, but I can't ever reach pi over 2. The same thing here. If I flip the behavior of the x and the y, in this function, the y values can get as close as you want to pi over 2, but they can never reach there. Same thing as you go to the left. You can end up with the fact that the arctangent gets closer and closer to minus pi over 2 as you tend to the left. If y is equal to the arctangent of x, what is dy dx? And we're going to do it the same way. We're going to approach this with implicit differentiation. So y being equal to the arctangent of x is the same as the tangent of y being equal to x. That means that d by dx of the tangent of y is equal to d by dx of x. And now using implicit differentiation, I'm going to get that the secant squared of y dy dx is equal to 1. And that looks pretty much exactly like before. So when we rearrange this expression, what we get is dy dx is equal to 1 over the secant squared of y. What is the secant squared? Well, secant squared of y is equal to 1 plus the tangent squared of y. So this is the Pythagorean identity that relates secant and tangent. And that means that dy dx must be equal to 1 over 1 plus the tangent squared of y. And now I can use the original defining equation because the tangent of y was equal to x. And so this is 1 over 1 plus x squared. So of all of the inverse trig functions, these two are the most important, the sine and the tangent. A thing that you might get asked to do with mixtures of tangents and arctangents and sines and arcsines and cosines and arccosines is to interpret expressions where you have to apply a trig function to an inverse trig function. For example, you might get asked to evaluate something like the cosine of the arctangent of x. Very common in this section of calculus texts to have to evaluate expressions that look like this. Now, this might seem like an expression that is as deep as you can go, unless you remember that what the arctangent does is it looks at a ratio of x and y coordinates and it spits out an angle. So the theme I want you to remember about these is that inverse trig functions output angles. Well, if the arctangent of x is an angle, then I could just write the arctangent of x is some theta. But if the arctangent of x is theta, then that means x is equal to the tangent of theta. And I know how to build a triangle involving the tangent of an angle. So what is the triangle that's associated with this equation? So here's where you get to remember your SOHCAHTOA, or however you remember it. If the tangent of theta is equal to x over 1, this is supposed to be equal to the ratio of the opposite side to the adjacent side on the triangle that you're looking at. And so the triangle that's associated with this is going to look like a right triangle. It's going to have a theta down here. And then the opposite side is of length x, and the adjacent side of that angle is of length 1. And so just by the Pythagorean theorem, you know that this other side must be x squared plus 1 in a square root. Now, what the question was originally asking you to evaluate was the cosine of the arctangent of x, which means that really we wanted to know the cosine of theta. So what is the cosine of theta? So if this is theta, then the cosine of theta must be equal to the adjacent side over the hypotenuse of this triangle, which is equal to 1 over the square root of x squared plus 1. And remember that the theta here, that is actually equal to the arctangent of x. And so the answer to the cosine of the arctangent of x expressed as a function without trig functions is 1 over the square root of x squared plus 1. And this sort of manipulation of right triangles is one of the ways that the trig functions and their inverses interact with each other. So now we need to look at what happens with integrals. We've got derivatives, we need integrals. And the two most important derivatives are d by dx of the arcsine of x is equal to 1 over the square root of 1 minus x squared, and d by dx of the arctangent of x is equal to 1 over x squared plus 1. The other 4 inverse trig functions you can find in a table in the textbook, and I'm sure you'll be asked to use them there, but they're related and very similar. If we know the derivatives, we know the integrals. Corresponding to the integral of the arcsine is the integral of 1 over the square root of 1 minus x squared dx is the arcsine. And the integral of 1 over x squared plus 1 is equal to the arctangent. Now I'm doing this on purpose where I'm mixing the notations here, the arc notation and the inverse notation, to get you used to the idea that these things are equivalent to each other, and that which one we use is really dependent on the practices of the field that we're working in. What is the integral of 1 over x squared plus 4 dx? So the problem here is that the 4 means that this is not part of the formula that we learned. We know that if I had the integral of 1 over x squared plus 1 dx, that I could write this as the arctangent. But I don't have a plus 1. I've got this plus 4. So what I'm going to do, the strategy that I'm going to use to look at this, is I'm going to force there to be a 1 here, and then whatever that does to the x, I'm going to use u substitution to fix it. This is a theme in these types of exercises. There's a formula you could memorize as well, but I think that's probably the worst way to go about learning this type of math, because otherwise you have to memorize so many formulas that it's easy to make mistakes. And I'd prefer that you understand the process. So step 1 is I'm going to force there to be a 1 right here, and I'm going to do that with factoring. So I'm going to rewrite this as the integral of 1 over 4 times x squared over 4 plus 1 dx. I'm allowed to do that. I can take out that number, and you can check that this is equal to the original thing just by distributing the 4 back inside. Now I'll go one step further and actually pull that out front as a 1/4. Step 2 is to notice that whatever the quantity was right here, it has to be squared. And this doesn't look like that because this has an x squared, but it's over this number 4. And I'd like to write it as some sort of quantity squared. And the way I do that is I just notice that this is the same as x over 2 squared plus 1 dx. And now I'm really close to having this in the correct form. Now what I can do is I can use a u substitution to finish this up. Let u be equal to x over 2 so that du is equal to 1/2 dx, so that 2 du is equal to dx. And when I make that substitution, what the integral turns into is 1/4 of the integral of 1 over u squared plus 1 times 2 du. And I can take that 2 and I can pop it out here with the 1/4, and that integral becomes the integral of 1/2 u squared plus 1 du. And now finally, this can be used. This equation right here, the fact that I know that this integral is equal to the arctangent, I have everything in the form that I need to use it. So this is equal to the arctangent of u plus c with a 1/2 out front. And then I can substitute back, and what I'll get is 1/2 of the arctangent of x over 2 plus c. And that's all finished.